ಇದು ಮೋಸ್ಟ್ಲಿ ಯಾಕಂದರೆ ಇಲ್ಲಿ ಝೂಮಲ್ಲಿ ಕೂಡ ಆಡಿಯೋ ಆನ್ ಉಂಟು ಸೇಮ್ ಸಿಸ್ಟಮ್ ನಮಗೆ ಟಿ ವಿ ಬೇಕಾಗಿಲ್ಲ. ಹಲೋ ಚೆಕ್ You don't worry about this.
I can completely ignore that.
YouTube so
Where will I be seeing the students?
Good question. Where are they? ಎಲ್ಲಿದ್ದಾರಾ ಮಕ್ಕಳು? ಅಲ್ಲ ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್
ಇವನದು ಕ್ಯಾಮರಾ ಆನ್ ಆಗಬೇಕಲ್ಲ ಮಕ್ಕಳನ್ನ ನೋಡಲಿಕ್ಕೆ.
ಓ
ಇದು
ಶೇರ್ ಆಗೋಲ್ಲ. Can you ask them to turn on their videos?
Ramya, could you turn on your video, please? What's that camera?
This is this camera. It's fine, don't worry.
That's what the students will be saying.
Yeah. It's okay.
I don't know.
Yeah. We're just figuring it.
ಈಗ ಚೇಂಜ್ ಮಾಡ್ಬೋದಲ್ಲ ಕ್ಯಾಮರಾ?
ಎಲ್ಲಿ? ಅದು ಆಲ್ರೆಡಿ ಆಬ್ವಿಯಸ್ಲಿ ಯೂಸ್ ಆಗ್ತಾ ಉಂಟಲ್ಲ.
ಎರಡು ಯೂಸ್ ಮಾಡ್ಲಿಕ್ಕೆ ಆಗೋದಿಲ್ಲ?
ಹಾಂ? ಇಲ್ಲ. ಒಂದು ಡಿವೈಸ್.
Or you could keep the laptop here. No?
Yeah, we could do that.
Yeah.
Now what? Once students come, that will automatically. We won't disturb your class, okay? In between, I might come and won't disturb you. Don't worry.
Okay. I'll keep it here.
Yeah.
So this obvious thing is going on in the background, right?
Yeah.
Okay.
Just ask them like if they're able to see your screen and they're able to hear.
Yeah. Okay.
Can you check some normally so that
Yeah. One second. Yes. Good evening, everybody.
Good evening, sir.
You can hear me clearly, right, Shreyas?
Yes, sir.
Yeah.
Screen.
Yes.
Is it visible also?
What about my screen, Shreyas? Can you see it clearly?
Sir.
You can read every bit of the question right there.
Yes, sir.
Yeah. All right. Yeah. Thank you. Just keep your webcams on. And I believe this is where I stopped in the previous class. I do not know why my face is at that angle. Anyway. So let's see, we are going to spend quite some time on this question here, okay? Because I believe this is one of those important kind of problems. I'm going to complicate it a little bit in the beginning, just to show you that it can be done in a simple way, alright? So I want you to spend some time on that, just look at it. A straight frictionless track terminates into a curved section in the form of an arc with radius r, subtending an angle theta at the center as shown. A block of mass m is given an initial velocity u along the horizontal section of the track as shown. Okay. Find the maximum height gained by the block in the subsequent motion, given that the initial velocity is large enough to make the block leave the track at the end. So what we are saying over here is that the initial velocity that we are initially giving, okay, is large enough to make the block move outside the track there. Okay, we are assuming that it's large enough. Okay, whatever large enough means. Right now we do not know what large enough means, isn't it? But intuitively we are saying it's large enough. Okay, now I want some help. Anaga, can you help me out? I'll guide you, don't worry. So in the beginning, look at the problem over here. So I see that the block is over here and it's just given an initial velocity, right? It is just given an initial velocity. So how do you give initial velocity to the body there? What do you do in the beginning? How, what do you suggest? Sorry?
Sir, could you repeat it, sir?
Yeah, so you can see that initially there is a velocity of u, isn't it? I'm asking, how do you give that initial velocity? Do you have to push it, or do you have to shoot it with a spring, or do some sort of apply some sort of force? Do you have to do that?
No, sir.
Why not? Did you understand my question? I'm asking, see, in the problem it's been given to me that the body has an initial velocity of u, isn't it? So when I start observing this particular case, this particular diagram over here, okay, I see that the body is at a velocity of u. Now my question to you is this: if it's at u, then it's at some point it must have been at 0, right? Does it have to be, or can it be at u itself? What do you think? Did somebody push it and it went from 0 to u, or was it at u in the beginning itself?
It is at you at beginning itself.
Yeah, it's at u in the beginning. I'm not so sure if I've understood my question. What I was trying to say is, if you find an object which is moving at a speed of u, do not pause it, do not say that it must have been at 0 speed, then somebody must have pushed it, and that's why it is going at speed u now. Alright? Need not be the case. It must have been moving since the beginning of the universe with the speed u. Alright? That also could be the case. You cannot find it out actually. Did somebody push it from 0 to the speed, or was it already moving at speed u? You cannot say that. Alright? So suppose suppose you find that the body is moving at the speed u, okay, you can only infer that the net force acting on the body must be equal to what? If the speed is constant, what can you say? At that moment, what can you say? The net force acting on the body must be 0. 0. That's all I can say. Alright? That's the Newton's first law. If you find a body that is moving at a constant velocity, then the net force acting on it must be 0. Alright? So here I see that there is one contact. There is a contact over here, so there must be a contact force, which we call as a normal force, isn't it? And then I know that there is automatically a force over here, which we call as mg. Now, given that the body is moving at an initial velocity u, constant velocity of u, I can infer that the normal force and the weight must be equal in magnitude. Right? So the net force is 0. Right? Okay. So there is no net force over here. This is Newton's idea, by the way, Newton's force. But let's look at the same picture from the work energy theorem point of view. From the work energy theorem point of view, let's see what this does this work out. Newton's laws work out over here. Newton's law says if there is no net force, then the body would continue with the same velocity. What does the work energy theorem say, Amaga?
Sir, the difference between the square of the initial and the final velocity.
Yeah, correct.
And the product of the mass.
1 second. Yes. Okay. Yeah, you were saying something.
So the work done is equal to half of m into the difference between the square of the initial and the final.
Square of the velocities, right? Or you can simply say work done is equal to change in kinetic energy, right? It's just that the work done, the definition of work done changes depending on the nature of the force. If the force is constant, then the work done is F into S, right? And if the force is variable with respect to the position, then you find that we'd have to calculate the quantity called work done. This is a mathematical quantity. Quantity of work done would have to be calculated as integral f dx, isn't it? So here, let me write the general form. Let me not say force is a constant. Let me not assume that. Let me try to write the most general expression, that is work done. Let me call this location as x1 and this location as x2. Okay. So work done in taking the particle from x1 to x2 under the influence of the net force, would be would result in a change in the kinetic energy. So this is half mv square minus half mu square. Please note that the kinetic energy, sorry, I messed it up, one second. The half mv square, the kinetic energy over here, that is the kinetic energy at the location x2, and half mu square is the kinetic energy at the initial stage, right, at x1. So we know that the net force is 0. We know that the net force acting on the body is 0, right? So the work done by a force of 0 Newton must be equal to 0, correct? Yeah. So this will give us that half mv square minus half mu square is 0. What does that imply? You can see what I'm writing, right?
So the initial kinetic energy and the final kinetic energy are equal.
Sorry, could you repeat that?
So the initial kinetic energy and final kinetic energy are equal.
Yeah, initial kinetic energy and final kinetic energy are equal. Moreover, if they are equal, yes, Banu, yes, kinetic energy doesn't change. But if they are equal, then this would imply that V is equal to U. What am I trying to say over here? I'm trying to say that Newton's law said that if there is no net force acting on the body, then the velocity will not change. The work energy theorem also says the same thing. If there is no net force acting on the body, then there won't be a change in the kinetic energy, which would also imply that there is no change in the speed. Alright? Yeah, one second. Okay, so no work done implies no change in kinetic energy. No change in kinetic energy implies no change in speed. Okay, what I'm trying to convince you is this, that Newton's laws as given to you in the previous classes and the work energy theorem as given now, right now, are not two different pieces of information. They are the same things. Alright? But in some cases it would be convenient to use a work energy theorem. Okay, now this would be one such case over here. So alright, so at least in the first half of the journey there, the work energy theorem seems to work. Alright. What about the next part? What about the circular part over here? What happens there? How do you calculate the work done now? Now this is a little bit hard. Let's see. One second. Let me draw this. Okay, that's supposed to be the circular drive, by the way. Right? Intuitively, can you tell me? Okay, Ramya, one second. Can you turn your mic on, please?
Yes, sir.
Let's say that the block is over here. By here, I can't simply say here. I need to tell you what here means. So here means at an angle theta as defined with respect to the vertical. Okay, that's what here means. Okay, so this is the radius r. Okay, so let's say the particle that the block which was initially moving with speed u is at that particular location. Now, what do you infer from Newton's law? Is it speeding up? Is it slowing down? What do you infer? Forget about Newton's law. What is the law?
Speed is decreasing, sir.
Speed is decreasing. Could you tell me why that's the case? Don't say it's going up. That's why it's reducing. That's true, but yeah. Could you just?
The net force at that point is not zero.
Net force at that point is not zero. But why is the speed decreasing? Net force is not zero. Agreed. So if I were to draw the force diagram, this would suggest that there is a force mg downward. Else, what other forces are there? Is that the only force? Can you hear me? Is my voice breaking?
Hello. No, sir, your voice is not breaking.
Not breaking, no? Okay. Yeah, what other force is there, Ramya?
Sir, normal force.
Normal force. There is one contact there, isn't it? And this normal force is always looking at the center there. Okay. And if you calculate the resultant force, so I can resolve this mg as, let's look at this angle here. That angle would appear here as well, isn't it? What do you call such angles? Corresponding angles, right? So the same angle theta would appear here as well. So this would be mg cos theta, and this would be mg sin theta. So I can infer one thing, that normal force and mg cos theta are one and the same. How can I infer such a thing? I'm saying that n must be equal to mg cos theta. Why do I say such a thing? How do I know such a thing to be true? Yes, Kenneth?
It doesn't go up perpendicularly
Exactly.
or neither down.
Yeah. Shaina? No. Equal and opposite force. How do I know that they're equal and opposite forces? I know because I look at the motion of the object. So Newton's laws, I have told you, right? You have to go back and forth. Acceleration implies force. Force implies acceleration. That is Newton's first law. Right? Now I look at the where the body is moving there. I see that there is no acceleration along the perpendicular direction. Along the radial direction. Therefore, there must not be any force along the radial direction. Okay? So based on the Newton's first law, the body is not accelerating in that radial direction there. One second. I think I've made a mistake. Can somebody correct me? I said there is no acceleration along the radial direction. I'm wrong. Let's see who can correct me. I made a mistake. I've made a mistake there. Can you correct me? Anybody? When you come to the regular classes, I'll give you a chocolate. What is my mistake? I did not think really. N is not equal to mg cos theta. N has to be greater than mg cos theta. Yes, Shreyas, do you realize the mistake?
No, sir, I didn't understand why mg cos theta must be greater than.
No, N must be greater than mg cos theta is what I'm saying.
Sir, is it because it is going to leave that surface?
Sorry, could you repeat that? Kenneth, very good. Kenneth, yes, that's the right answer. Yeah, sorry.
It is going to leave that surface, sir.
No, I did not hear you. I'm sorry. I'm growing
Sir,
old.
is it because it is going to leave that surface?
It's going to? No, what's going to happen later, you do not factor in what's going to happen later during the motion right now. Right? So who knows what's waiting for the object later? So object doesn't know what's out there before it has reached there, isn't it? So because it's going to leave the surface later, it's not going to decide its motion now. That would be a very strange world to live in. Right? N must be greater than mg cos theta. That's your clue. I'm telling you which force must be greater. Alden, very good. Yes, you're right. Can you tell everybody what my mistake was? Yes. Can you repeat that, Alden? Oh, your mic's not working, Alden. Kenneth, yes. Can you repeat that for everybody? What I'm talking about? Whatever you said in the chat.
due to centripetal acceleration.
Yeah, centripetal acceleration, right? See, the very fact that the particle is going in a circular path means it is accelerating towards the center. It has to, right? So if I see, that's my mistake. So if the particle was over here, it would have gone along the straight line if there was no force acting on it, right? But what's happening? It is being constantly pushed towards the center. See, it would have been over here, but it's been pushed towards the center. So at some later stage it should have been over there, but since it's let me do that in another color. It's been pushed towards the center, you see. And look at the size of those arrows. Those are the displacement vectors, isn't it? Look at the size of those arrows. The size of the arrows goes on increasing as the body is going forward and forward. You have seen the way the displacement vectors increase in the case of accelerated motion, isn't it? The size of the arrows goes on increasing, and you can see that over here also. So there is an acceleration along the radial direction. So n is not equal to mg cos theta. Is that okay? So I cannot write this equation. So I cannot write that equation. But let's see. So now let's look at the advantage of the work energy theorem over Newton's laws. Okay. So if I was going to apply Newton's laws, I would have to consider that there is a centripetal acceleration, because the centripetal acceleration would give me v square by r. Centripetal acceleration is v square by r. From that value, I can figure out the v value. V value is what I require, right? Speed at the speed with which the body leaves the track. That's what I require. So I'd have to apply Newton's laws in two directions and see. Now, about the work energy theorem. I talked about the work done. I mentioned work done is equal to force into net force into displacement. Right? And I had also mentioned in the previous class that if you tie a thread to Len, where is Len? Len, where are you? Okay, Len is having some mic issue. Let's tie the thread to Kenneth. Kenneth, if I tie a thread to you like this, now which way can you access? Now there is a direction over here, Len, that you can go in without having to do any work. Which direction is that, Len? Sorry, Kenneth. You can go in some direction without having to do any work. You don't have to do any work there. I'm relying on your intuition, I'm not relying on mathematics, because doing it would be very hard. Sorry?
Circular path.
Yeah, along the circular path. Right? Circular path, because if a force is pulling you in a certain direction, alright, if a force is pulling you in a certain direction, it has no effect along the perpendicular direction. So any force cannot affect the motion in the perpendicular direction. So Kenneth is free to move in the tangential direction like that, and no work would have to be done against the force to do that. This is why I told you planet Earth. If you look at the motion of the planet Earth around the sun, at every point it is going tangential to the force vector. Right? So therefore there is no work done in the planet going around the sun. If there is no work done, there need not be any energy spent. Alright? So what I'm saying is, if you're all the effects of the perpendicular, now look at this, there might be a bunch of forces acting on this body. Let's say there are a bunch of forces acting on this body, and as a result of all these forces, the body is displacing along the x-axis. Alright, bunch of forces. Let's say there are 36 or 37 forces acting on the body, but the resultant motion is along the x-axis. So what is the work done by all these forces? Now you know the same logic can be applied over here. So if you pick out a certain force, let's say ith force there, I can make a 10th force, let's say. You pick out the 10th force and you resolve that into two components. resolve that into two components. So when you consider the work done, okay, you can ignore the perpendicular component. You can ignore the perpendicular component. You pick out the component that is along the displacement only. Alright, and that is the dot product, isn't it? You pick out the dot product. You pick out the component of the force that is along the displacement. Remember the dot product classes? What does the dot product do? Dot product basically picked out the component of the first vector along the second vector. Or you can think of it like this. Pick out the component of the second vector along the first vector, this one direction. Right? So when you take the dot product, you pick out the component of the force that is along the displacement. Okay? So that would be the work done. Here also we are going to do the same thing. Here also I am going to do the same thing. I am going to pick out the component of the, even though net force is not this, one second, sorry. Net force is not mg sin theta. There are other forces, n minus mg cos theta, which is pushing the particle towards the center. But I see that the displacement is along the tangential direction over here, right? Displacement is along the tangential direction. So I'm going to pick out only the component of the force, net force, which is along the displacement. And that happens to be this mg sin theta. Okay? Now, what is the work done here? What would be the work done? Work done is equal to the component of the net force along the displacement, and this work done is going to change the kinetic energy. Is that okay? Now let me give you another intuition. Now Ramya told us that as the body goes from theta is equal to 0 to theta is equal to 30 degree, its speed is decreasing, correct? Its speed is decreasing. Speed along the path, it's decreasing. Now which component of the force can decrease the speed? Ramya, which component of the force can decrease the speed? Can the radial component decrease the speed?
Yes, sir.
Can this component, if I push the object this way, can I reduce the speed in this direction?
Yes, sir.
You can. Something is going in a circular path, look at that, and I'm trying to push it this way. Will that reduce the speed in that direction? Can the perpendicular force, can the radial force decrease the tangential speed? Yes, Shaina, we are changing the direction. When you are going in the circular path, the direction keeps on changing, isn't it? But look at what's on the other side. Look what's on the other side. We have a speed component there, isn't it? We are looking at the change in the speed. So I'm asking you, can the radial component of the force result in change in the speed? Ramya, you don't agree that radial direction cannot change the speed along the tangential direction? It's okay to say I don't agree. I can convince you. See?
Can you repeat the question?
Yes. So here's the object. That's the object there. Okay. And there are a bunch of forces acting on this object, isn't it? There is a resultant radial force, which is n minus mg cos theta. N minus mg cos theta. Agreed? That is providing the centripetal force. That force, the radial force, is providing the centripetal force. That's the force that is pushing the object towards the center, isn't it? So I can say n minus mg cos theta is providing the centripetal force, which is mv square by r. Okay. Is that okay? Now, the question is this: can this force also reduce the speed? Can it reduce the speed of the particle? What do I mean by speed? It's going, one second. Yeah. Yes, it's going in the sorry, what am I doing? It's going in the tangential direction there, right? At every moment the velocity is tangential. So can this tangential velocity be decreased because of the perpendicular component?
Yes, sir, it can decrease.
How? How do you say that? No, I want some answer from you. Why do you say that it can be decreased? I want to know why you are saying that. See, velocity along the tangent, can it be decreased by a force along the radius? What is your reasoning?